All right, we just got the recording started for this this live session. We are going to finish tonight at 11:55 p.m. Week number 3. And with week number 3, we are going to finish module 102. So this live session is there to wrap up, actually, module 102, which was on conditional statements. So anytime you have any sort of question, feel free to interrupt. There are different ways you can do that. You can just take the microphone. We have multiple speakers allowed. You can use the hand raised icon like I'm doing right now. The button for that is right above the participant list. Or you can just type something, in the chat window. Okay. I try to keep an eye on the chat window so that if there are questions that pop up, I finish my sentence and then I address them as soon as possible. And hello, Gustavo. So don't hesitate to interrupt anytime during the recording. The only caveat is that, well, your question will be recorded. So if you don't want that, what I would like you to do is to hold your question until the Q&A section we'll have afterward. Once I'm done with the little overview that I'm recording right now, I'm going to stop the recording and I'm going to stay around so that you can ask me questions so that we can meet one-on-one if you need personalized help. Okay? So don't hesitate to hang around and after the session and ask your question there if you prefer. So the objective of those live sessions that are going to wrap up a module is twofold. One is to have that Q&A at the end so that every student can come with their problem and I can try to resolve them before we are done with the module. And then the other thing is to try to map everything that we learn in those modules to the different programming skills that we identified already. Okay, remember we identified that what people refer to as the one programming skill generally can be broken down into different things like tracing code, implementing code, testing, refactoring, debugging, and designing, okay, and implementing. I don't know if I already mentioned that one. So all of those skills are different things that you need to learn. So it's good to isolate them. It's good to identify them. So what I'm going to try to do in those wrap-up sessions is kind of connect everything that you are learning during the week to each of those individual skills. Sometimes the connection is going to be trivial. Like for example, implementing in Raptor, there's really not much I have to say about it because implementing is straightforward in Raptor. Raptor is designed to be easy with respect to that skill, okay? But there are other skills like for example testing, refactoring, that we're going to talk a lot about in this session, for example, today, okay? So, and that objective in itself, linking the material to the skill, also has a second purpose, which is to prepare you for the exams. When you take your exams, you are going to see that the exams are divided in questions. Each question relates to a specific skill. So by revisiting material, and trying to link it to each of the specific skills, I'm trying to prepare you better to the exam. So as the day of the exam, when you see the question, like you've seen already in the template exam, you are not going to be surprised in any way. Okay, you are going to know exactly what to expect for a tracing question. You are going to know exactly what the tracing skill encompasses, and so on, so forth. Okay, so let's get started. Let's get started with the highest level skill, design. So this is probably one of the hardest skills, but fortunately, with the lecture that we had this week, we don't have that much to worry about regarding design. Okay, so let me grab a pen here. The main thing that the lecture did in module 102, is to teach you about the selection statement. Okay, selection statement is relatively easy to understand, especially in flowchart form. Okay. You come this way, the execution of the program comes this way from the top. You have a question here, which is, we have seen that in the lecture, okay, it's a Boolean expression, okay? So you have a Boolean expression, which is pretty much a question regarding the variables that we have stored in memory. So is, for example, x equal to 42, that kind of stuff. And then you have two possible outcomes. One outcome is, the answer to the question is yes or no. Yes being often interpreted as the Boolean expression is true, no as it's false. Okay, and depending on which one it is, you execute this part of the code or that part of the code. Okay, and then no matter what you do, you end up in this part of the code here that I represent by a triangle. Okay, so this is outside the if statement right here. It's past the if statement. So you just choose one or the other path. So it's relatively easy, right? Now the main question when you try to design a solution to a problem, the main question you're going to ask you over and over and over is, well, the very first question is, do I need an if statement? So far, what did we study? We studied what? 1, 2, 3, 4 different statements. Okay, we studied the get statement that reads something. Okay, we studied the put statement in Raptor that displays something on the screen. We studied the assignment, which I'm not going to abbreviate, assignment statement, okay, variable x, which is 42, and now we are starting with the conditional statement. I mean, module 1 or 2 was all about the if and the if-else statement, which in Raptor is always the same thing. It's that thing here, okay? So we have like 4 statements. So how do you decide first that you need an if statement? Every time you need to test something, okay? All of those things here do not perform any tests, do not perform any conditional execution of code, you know, if this is true, then do that, if this is false, then do that. So it's really easy to identify that you need an if statement instead of one of those get, put, or assignment statement that we studied in the previous module, okay? Now the second level of difficulty is if you need multiple if statements, how do you arrange them with one another? And that's what the lecture was really focused on explaining, okay? Meaning that you can have an if statement here, okay? Sorry about the bad driving, followed by another if statement. And we refer to those in the lecture as serially arranged if statement. So you test one thing here, there's an outcome, true or false, and then independently, and this is a key word, independently of the part of the code that you executed with this first if statement, you repeat another test, probably a different test here, okay? And there is an outcome, true or false. And that's it, okay? That's the easiest, the part that generally people understand without any problem, okay? Now, the one that is a little bit trickier, and you'll see in this session that when we talk about refactoring, that this can get really nasty actually, is if you have nested if statement. So here's an example of a nested if statement. Those of you who did their exercise as they were supposed to, you are familiar with the kind of diagram because you encountered it with the Palo Alto Squirrel problem, okay, apprenticeship exercise A09. So this is an example of nested if statement that can go on infinitely. You can have another if statement, if I can find my pen, there we go. You can have another if statement here, another if statement here, another if statement here, another one here, so you could have like 2 nested if and then 2 serially arranged if, okay? So this is when generally you are called upon to think a little bit more deeply about what you are doing, okay? If statement is easy to understand, but then combining if statement is really where, for a novice programmer, the difficulty generally lies, okay? So again, the lecture tried to explain those patterns. So to help you with the design skill, what you need to do is you need to familiarize yourself with those different patterns, okay? Let me take a couple of examples of what an if statement can do for me. Okay, when I'm done with that, let me look, for example, of what 2 serially arranged if statement can do for me, and then when I'm done with that, let's take a look at 2 nested if statements. Once you have covered those 3 possibility, a single if statement and then 2 if statements that are either serially arranged or nested, then you're ready to do anything, okay? I want to remind you, learning to program doesn't mean that we're going to show you every possible program in the world, and then you are going to memorize it and memorize that it solves a specific problem, and when you face a new problem, you just have to remember what program solves it. No, that's not programming at all, okay? Programming is about learning what certain building blocks or patterns do, and then learning to recombine them. So that's exactly what we did in module 102, right? Number 1 up here is learning about the building block. How does one if statement work? And then the rest of the lecture was about, well, what are the different ways to recombine 2 if statements? And we saw that there is only 2 ways. But then, with those 2 ways of recombining if statement, you can generate an infinite amount of programs. So don't let that overwhelm you, okay? Don't attempt to learn by heart every single possible combination. Just learn the building block and how to recombine 2 of them. And then you can generalize that to whatever you need, okay? Like I said in this example here, if I was adding an if statement right here, okay, what would we have? We would have one here, one if statement nested with another if statement nested inside of it, and then we would have two serially arranged if statement one after the other, both nested inside that first if statement. Okay, and that can repeat, the structure can repeat itself infinitely. Okay, so the decision point is really, when do I need to serially arrange, when do I need to nest? Okay, so this is it for design. Okay, I'm not going to, I kind of provided you with a sort of recap of the lecture video, but I'm not going to repeat what was already in that lecture video. I just wanted to refresh your memory before we go on to other things. So it's really a matter of pattern matching here, matching your problems into those little building blocks that you have been learning with the design skills, pretty much. Implementing, I'm getting rid of the easy to summarize skills right now, because we have two skills on which we are going to spend 90% of our time this session. The second skill that's relatively easy is the implement skill. If I have some pseudocode that say if n lesser than 42, then dot a message, okay, something I want to display on the screen, else dot a different message, okay. And if I'm using some pseudocode, so it's English, but it's English formalized to look like a programming language. Okay, so I have some keywords that I use all the time here: if, then, else, and if, that mark the end of the if statement. So if I gave you this after explaining, those keywords, which is pretty trivial, if I gave you this and I ask you to implement it in Raptor, like I said before, this is really where Raptor shines, because we have like a if statement, right? And the if statement condition is going to be n lesser than 42, and then let's call that 1, let's mark it 1, let's call that 2. If my condition is true, I do the put statement marked as 1. If it's false, I do the put statement marked as 2, and then this is my end if here. Okay, I'm done. So the reason for which for module 101, 102, 103, I'm not going to have much to say, if anything, about the implementing skill is because Raptor makes it so easy to go from there, what's on the left, to what's on the right. So the implementation doesn't allow you to make syntax error, doesn't allow you even to put an assignment where it doesn't belong, like trying to shove, an assignment statement here inside the condition. Not going to happen. And impossible, just impossible. Okay. So Raptor, because of its visual nature, prevents you from doing 99.999%, if not 100%, of the mistake that you would usually do in the implementation part. So when we start module 201, okay, when we start talking about Java, then we'll talk more in detail about implementation. But you're going to see that for 101, 102, 103, implementation is going to be trivial, and really I think this is the last time I'm going to even list it during those live sessions, because there's really nothing to say about it. So we have talked about the design skill, okay. We have talked about implementation skill, trying to kind of discuss what in the current module was related to this, and you can see implement really has very little there. Let's talk now about tracing. And to illustrate the tracing skill in module 102, I'm going to use the last apprenticeship exercise, which was the Palo Alto Squirrel, which we use also in the practice exercises. So this is A09, sorry, little bit of French there, I didn't mean to do that. This is A09, this is Squirrel, the Palo Alto Squirrel problem. So just to review that real quick, what is the Palo Alto Squirrel problem? Well, we read two variables from the user, two values that we store in two variables. The first value is the temperature, so we expect the user to provide us an integer or a floating point, doesn't really matter here. And then the second is a variable named summer, and summer will be equal to 0, meaning it's not summer, or 1, meaning it is summer. So we ask the user to provide a 0 or a 1. Okay. There was a very good question in the forum this week about whether, because I ask you often to make your program more robust. So for example, this is not a robust version of the Palo Alto Squirrel, because if the user types, for example, a temperature that's negative, that doesn't make sense, you know, or that's too big or too small to be realistic, we don't detect it. And same thing for summary. The user, we tell the user, please enter 0, 1, but if the user enters 3, our program is not ready right now to just say, you know, I cannot process that input, stop, goodbye, okay? So that would be what the robust version of a program is. But then the question in the forum was like, well, I can intercept, you know, out of range values. Well, how am I going to detect if the user typed a string of characters? If the user types, you know, for example, a floating point when I expect an integer. Like summer, for example, instead of doing 0, 1, the user types 0.5. So what is it, okay? And I responded in the forum, so I refer you to that. But it's a very good question. What we are going to do in this class, and those of you who are going to move on to IT program design, will do the same thing. In this class, when we talk about testing, and we talk about testing based on user input, we always simplify by assuming that the user gives us the right data type. If we ask an integer, the user provides an integer. If we ask a floating point number is given to our program. If we ask for a string of character, which we are going to do, you know, when we start playing with Java, then yes, we are going to get a string of character. However, we allow provisions for the user giving us a value out of range. For example, if I ask an integer between 1 and 3, yes, I will get an integer. That's the assumption for this entire class. But this integer might be 0, might be 1, 2, 3, 4, 5, minus 1, minus 2, so it may be out of range. The value may be out of range, but the value will be always of the right data type, okay? And again, refer to the forum if you are curious about why we make that simplification. Bottom line is that to be able to really verify the user input, sanitize it properly, like you would do if you were coding a web form, for example, we would have to take the user input as text. Even if the user input enters 22, even if the user, enters a value like 21 or something like that, we would not read it as an integer. We would read it as a text. And then we would do something called parsing of the text to identify exactly what was given to us. And that is something that you are going to be, I would say, ready to work on by the end of IT program design. Okay, but it's way too early to introduce it right now. So that's why we make that simplification. So very good question there. Back to our Palo Alto Squirrels. Once we have this data from the user, what we do is we do a first conditional test here. Okay, so is it summer, yes or no? So 1 means yes, okay. No means 0 means no. And depending on whether it's summer or not, we check the temperature to be within a certain range. Okay, so both this if statement and this one check that the temperature is between an upper and lower bound. Here, the interval that is acceptable for the temperature is 60 inclusive 100. Okay, inclusive as well. Here it is 60, 90. Okay, so in each case, yes or no, is it within the range or not? And if it's within the range, the squirrels are playing. Okay, if it's not within the range, then we display a message that says the squirrels are not playing. All right, that was apprenticeship A09. Okay, refer back to the video if you want to see step by step how to build it. Now, what I'm interested in doing here, I'm interested in looking at how I can take a program that works. Okay, this is a I hope that, yeah, there should be a working version of the program, or else I'm going to get in trouble. So I want to take a program that's working, and I want to trace it. I want to illustrate what I would expect at an exam, you know, if I ask you to trace this program. So generally, depending on how the TA is preparing the exam, we can have numbers, like I did in my example, okay? Last week when I illustrated tracing for the first time, you know, I used numbers like that for each instruction. Or we can have any other way to represent a specific step in the program, okay? So we could call this 1, 2, 3, then we could call this 3.1, this if statement step would be 3.2, then we would call this 3.1.1. You see the scheme there, okay? 3.1.2. We number things so that we can uniquely, identify exactly the part of the code that we're talking about. Okay, so any scheme will work. Anything will do. Okay, maybe we don't need to identify all the parts. I don't know. But the idea is that we always have a way for you to tell us what step of the program you are currently on. Okay, and this is what you're going to use in those tables. The first the first column of the tracing table is generally the step or the line number of the program if we have numbered line and stuff like that. So this is pretty much what is being executed right now. So where do you start? Well, if we want it to be, completely exhaustive here, I would add a 0 and a 4, 0 being where I start, 4 is being the end statement. So I start with statement 0, which is a start statement. Okay. TMP and summer, these are the two variables that we use. They don't have any value yet. Okay. So generally, depending on the instruction, you can just leave like blank, or you can put question marks. Okay, doesn't matter. Then we do number 1. Step number 1. Step number 1 is a get temperature. So I prompt the user to enter the temperature. Let's say the user enters value 75. Okay, just to have a value. Summer has not been changed. So generally, when a value doesn't change, I just leave it blank. That avoids the table to be overcrowded with information, like seeing a bunch of question mark where really nothing is changing. So I leave it blank when the variable value doesn't change, and then go to the next step. Next step is step number 2. Same thing for summer. So let's say that we provide the value 0 for summer. So I write down what has changed. Okay, the value for summer has changed. I don't write anything for temp because it did not change since the previous line, and I keep going like that. So what happens now? Summer equal 1. Okay, so this is going to be step 3. Step 3, I'm right here, and I'm testing summer equal 1. Well, it's good to have a column like notes sometime, at least when you do it by hand, just to practice, to allow you to take notes on what happens, like what is this expression evaluated in. I mean, if statement, summer equal 1, that's false, so I write here that it evaluates to false. That helps me, keep track of what's happening pretty much. Then what do I do? Well, if it's false, that means that so far I've been executing my code sequentially. Okay, one statement after the other, and now I'm branching to this part of the code because my evaluation of the condition at step 3 tells me that this condition is false. So I follow the no branch, okay? And I find myself with another if statement. So I am now at statement 3.2. And again, I'm trying to evaluate whether temperature is between 60 inclusive and 90 inclusive. That's true. So I keep track of this and I say, yes, it is true. Notice that I haven't changed any value in my variables, so I'm not going to keep writing again 75.0 every single line, okay? So now I know that this is true, which means I'm going to follow this branch of code right here. And that leads me to 3.2.1, where I display the squirrel are playing, which I'm going to represent with this, okay, a check mark, like I did here on the bottom. And then I reach 4, and then my program is done. Okay, so that would be an example of a tracing. So obviously, depending on what value you input for temperature and summer, you are going to end up navigating different branches of this simple program. Okay, and you can see right now, just taking a quick look, you can see that there are 4 different possible paths in this program. Okay, there's a first if statement that gives us 2 possibilities, 2 different paths, right and left, okay, true or false. And then in each of those paths, we have 2 more possibilities. So a total of 4 possibilities, 4 different ways to execute through the code in this program, 4 different, what we are going to call them is execution paths, okay. So when I introduced testing to you, I mentioned execution paths, but really didn't make much sense because back then we didn't, it was before module 101, we didn't even know really a Raptor, so I introduced like just a few instructions in the Raptor, and then all those instructions were sequential. There was no branching, there was no choice. So pretty much I had only a sequential code to show you. And the concept of execution path is really limited when you have only sequential statement, because guess what? You start with statement number 1, then you go to 2, then 3, then 4, then 5. When you reach the end of the program, you're done. There's one path. Now here we have a mix of sequential statement, like the get and the to get instruction at the beginning, and a mix of sequential test statement with conditional statement, which open choices. Okay, so they are always part of the code that are not going to be executed. Every time I run my program, there are going to be 3 out of the 4 paths that are not executed. Okay, so that's pretty much it for tracing. Let me make sure I didn't forget anything that I wrote a note on to mention. No, we're good. So this is testing. Now this is tracing. Now let's talk a little bit about testing. So let me grab real quick. I'm going to copy back this Palo Alto Squirrel example. Okay, so this is the same code. Okay, it's not a new code. It's exactly the same program. Now, what I want to talk about are 2 concepts that are really important in testing. And again, I mentioned them before, but without the support of having programs that are complicated enough, that offer enough choices in terms of execution path, then testing looks like an exercise in futility. Okay, but now that we have those branching instructions, testing is much more interesting, and especially the concept of code coverage becomes really important. So I'm going to write this down. Okay, there we go. Code coverage. Well, what does code coverage means? That means that in my previous example, this is a path that I followed through the code, right? All right. One of the 4 possible paths of execution. So you could say that what I did when I traced with a value, what was it, 75, and then for summer I said 0, you could say that this was actually a good test, right? This is a good test for my program. It makes sure that this particular path does what it is expected to do based on the requirement. However, the problem with this is that if there was a problem here, a bug, for example, instead of saying the squirrels are not playing here, I say the squirrels are playing, and I'm wrong. Or if there was a bug here, or if there was a bug in any of those statements that didn't get executed, all of that, what we call sometimes dead code, okay, code that didn't get executed during this one trace, during this one execution, during this one test, okay. Well, all of that dead code, I can really not say anything about it. So this test here, 75 and 0 as input value, allows me to check that one of the conditions expressed in the requirement has been successfully implemented, one of them. But that's very limited. So the idea of testing is that we want to generate enough tests, enough values that we provide our code, and then verify that the expected, that the outcome is actually the outcome that we expected. We want to generate enough of these so we are capable to guarantee that all of our code has been executed. And I think that I just got the screen sharing disabled by Blackboard Collaborate. Thank you for that. I'm going to stop the sharing, restart it, okay, just to make sure. Because generally what happens is that when this happens on my end, on your hand you can still see the screen, but the screen is frozen. So we don't want that. I want you to stay with me and be able to follow as we are going to move through those slides. So let me move this out of the way. Okay. Alright, so let me know if you are not capable to actually view my slide here, okay? If you don't see anything being scribbled, like for example right now I'm scribbling a bit, okay? If you don't see that, let me know and I will make sure that I reset this thing. Thank you, Philip. Okay, cool. I wanted confirmation there. Alright, so we were talking about dead code, right? Before this rude technical interruption. So we want to avoid having dead code. If I have 5 tests and none of the tests, for example, trigger this branch of my program, well, that's not a very good test suite. Okay, that's not a very good. You'll hear the term test harness. Okay, this is not a good list of tests, pretty much. Okay, it doesn't trigger every possible part of the code. So at the very minimum, I want to trigger every part of my code, and sometimes I have to trigger the same part multiple times to make thorough test. Okay. But at the very minimum, I want to trigger everything. So what does that mean here? Well, let's take a look. We have several if statements. Okay, we have a top. I would call it the top if statement. So this is this guy. Okay, the guy that tests summer. Then we have a left if statement and a right if statement. Okay, so this would be the left if statement, this would be the right if statement, this would be the top if statement. Okay, so what can happen here? Well, the top if statement can be true or false. Okay, easy enough. So let me write here. I'm doing pretty much a truth table, okay, as you've seen in the lecture video. So my top if statement can be true. If my top if statement is true, then the left if statement can be true or false. Okay? So these are all the possibilities. There are two pretty much outcomes, true, true, or true, false. And then the right one, well, doesn't matter. It's not even executed. Now, if my top if statement is false, the same thing can happen, but this time with the right if statement. It can be true or it can be false. Okay? Again, two paths. Okay? So a total of 4 paths. That's what we discussed about. And in that case, in those two cases, actually, the left if statement doesn't really matter much. What is the expected outcome in every of those cases? Well, let's see. When it's summer and I am within range, then the squirrels are going to play. So I'm going to mark that as a checkbox, okay? And then if it's not within range, if the temperature is not good, they don't play. If it's not summer, but we're within the range for not summer, then they play. Otherwise, they do not play, okay? So right now, what we have here is we have kind of an outline of every possible path, execution path, but instead of drawing them on the Raptor flowchart like I did before, I'm making an inventory here of everything that can happen in those 3 if statements. Okay, so we have our 3 if statement here, 1, 2, and 3. Okay, and we have pretty much a truth table of everything that can happen. All right. So now that's not exactly giving us test yet. Okay, it's giving us the profile of the structure of our code, all the execution paths that are within, and it tells us what we need to test to guarantee code coverage. So if I have one test for the case where the top if statement is true, okay, and the left if statement is true, if I have one test for this, one test for the next line, one test for the third, and one test for the fourth, then I know that I will have code coverage. So that's one of the important things in testing. Now, the other thing that we talked about is boundary testing. Okay, and the way that we talked about boundary testing so far is by saying that, okay, let's say that that a program, we're not going to worry about the implementation, so we're not going to worry about how the program gets the job done. But let's say that I ask a program to accept a value between 1 and 3 for a variable. Okay, so if I enter 1, 2, 3, the program keeps going, does something, perfect, it works. If I enter something different than 1, 2, 3, then the program tells me, no, you made a mistake. So that's the behavior I want for my program. So if I want to test this kind of situation, how many tests do I need? Well, I could go the exhaustive route, okay, 1, 2, and 3. I'm going to test for 1, test for 2, test for 3. Does that guarantee me actually that my program is working? Any thought? Somebody on the chat window? Okay, so I have different opinion. Well, actually, I don't have different opinion. Everybody seems to be saying, yes, it guarantees my program works. Okay, so yes, if I test 1, 2, and 3, that's exhaustive testing, my program works. Okay? Well, no. For those of you who are interested, I really suggest you you look up epistemology. It's a philosophy discipline, so some of you are going to be like, why is he talking about philosophy? You know, I'm not a philosophy major. But interestingly enough, it's actually the discipline that is curious about answering the question of what is knowledge, what is, you know, certain knowledge, truth, etc. What is the pretty much the scientific validity of a statement. Okay, so it's almost a study of science. Okay, at a very high level. No problem, Philippe. Don't worry about it. So, okay, I'm trying to catch up with the chat window at the same time. So the reason I was saying that is because epistemology is actually interesting in and by itself, but it's also pragmatically interesting when you talk about testing programs. Okay. In this case, let's say that my program. Okay. So this is what I expect here. I'm trying to desperately find my cursor. Okay, there we go. This here is what I expect the program to accept, okay, as valid input. But let's say that I implemented my program and I did a mistake, okay, and really what I did is something like my program accepts anything between 0 and 4. Here's the interesting bit. This version of the program here, the bugged version of the program, is going to pass the test with 1, pass the test with 2, pass the test with 3. So what are we missing? What other values would you test? 0 and 4. Very good. Okay, so 0 and 4 is acceptable. Some of you might have said, hey, what about 5, 6, 7? Because, you just went through an experience here where you had all the numbers within the range, and that didn't prove anything. So maybe some of you are thinking, and that would be a logical thought, maybe you are thinking, well, there is, a lot of numbers beside 3, over 3, and there are a lot of numbers, below 1. So maybe I should test them all. And this is where you start feeling that exhaustive testing is really limited in practice. It sounds good. If you are capable to do exhaustive testing because you have only 3 possible cases to test, why not? That can be, that can be good. It's a good way to be sure. But most of the time, what you have to do and what I expect you to do during the exam is to be smart, to work smart, not hard. So working hard would be all the tests, all possible tests that you can feed your program, all possible output, and then check it out. That can become really fast impossible to track. And even on this trivial little example, okay, you can see how you would have 32,000 numbers or so, above 3, 32,000 number or so below 1. That's going to be, what, 64,000 tests just for this little aspect of one little program, which is accept a value between 1 and 3. This is crazy, right? We cannot do that. So instead, let's try to work smart, okay? What does it mean to work smart? It means doing boundary testing. And this works only assuming that your program implementation does something that I would say is linear. So if I test successfully, what I mean by linear, I'm going to explain. If I test successfully this end of the interval and this end of the interval, what I mean by linear is that your program implementation will guarantee that anything between those two extreme values is going to be okay. How does that work? Why can't we guarantee stuff like that? Well, look at this if statement here. This if statement is saying if temperature is greater or equal to, and I cannot read now that I scribbled over it, there we go, and temperature is less or equal to 100, okay? If you look at this, what can go wrong with this? Well, this number could be wrong, this number could be wrong, or this logical operator could be wrong. Maybe we use or instead of and, okay? But these are really the 3 things that can go wrong with this, as long as we are comparing a temperature here and here, the same temperature, okay? So we use that knowledge. We use that knowledge to say that the only thing we can do wrong is things like that, for example, where we are off by 1 because instead of greater equal, we use greater than, okay, greater strict. So we can be off by 1 like that. We can be off by 1 because we use 61 instead of 60. So under the assumption that these are the kind of errors that happen when we check the validity of a range, then we can allow ourselves to test only 1 and 3. Okay, we test the boundary of the range. But then, as Eric suggested, we need to also test, the negative, the things that should fail, to make sure our program distinguishes clearly between the interval that's valid and any other possible value. So again, can we go and take every possible value? Yeah, we probably could, but this is going to be silly and this is going to be really not practical. So instead, we use the same linearity assumption to say we're going to test 0 and 4. So in other terms, when you test, let me write it here somewhere, when you have an interval that is x and y, What you want to test is x, y, then x minus 1, y plus 1. So the lower value that is acceptable, the upper value that is acceptable, then the first unacceptable lower value, and then the first unacceptable upper value. And with that, you really nail it down. Now, you really identify the boundary between what is accepted, what is not accepted. Okay? So what does this have to do with what we are dealing with here? Well, let's go back to our test table here. Let's say that now I want values for input. Okay, because it's not really a test table that I have here. It's just a table that tells me, hey, these are your if statement. These are all the execution paths and what I expect them to do, okay? But I haven't talked the same way that I introduced tests before about values for variable. I haven't shown any value for any variable. So let's fix that, okay? Let's transform this into a real test table. The first thing is the variable summer, which I'm going to abbreviate by sum. And then the second thing is the variable temp, which I'm going to abbreviate, variable temperature, which I'm going to abbreviate with temp. Okay, so what's happening here? Well, if I want the top if statement to be true, that means summer is 1. So here, all of those cases, summer will have to be 1. Sorry, I'm going a little too fast here. Those two first cases where the top if statement is true, summer is going to have to be 1, and then summer is going to have to be 0 so that the top if statement is false. Okay, so I've just looked at those two true and false here. Now, what about temperature? So temperature relates to the left and right if statements. So, okay, let's see. If I have the left if statement true, so that one here, right here, I can have that with a temperature of, well, 60. Okay, that works because the interval is between 60 and 100 inclusive. But I can also have this with 75, with 78, with 80, with 90, with 100. So I'm going to take the two boundaries, okay, the two acceptable boundaries, upper and lower. And this here means that for this one line, I have two valid tests, okay? So one execution path, two tests to make sure that I trigger that execution path when I have a valid value, okay? What about the next line, where the left if statement is false? Well, again, you know, I could use a lot of different value, but what I want to use, based on the principle of boundary testing, is the first value that's going to cause a problem for the lower bound, and the first value that's going to cause a problem for the upper bound. And now you should get the idea of what we're doing here. Okay, so I'm going to go now to the part of the table where the top if statement is false, meaning summer has been set to 0. And then I'm going to look at the right if statement. And this is exactly the same thing, okay? Except that now the interval is 60, 90. So these are the value I want to test. And to trigger this path where the second if statement on the right is false, then I use the boundary value that cause the first boundary values that cause a problem. Okay, so this is very important, and this is the first time I can actually explain to you really what I mean by code coverage, and you can see boundary testing, but you can see it in a different context. Okay, it's still the same idea that with intervals. Okay, and proof is that we have an intervals in this code. We have several intervals in this code, but it also shows you how it interacts with if statements. Okay, so that's what's important. If I look at the execution path, I could come out of there and say I need only 4 tests. Now, if I look at execution path, but inside of each execution path, I look at the boundary that makes those conditions true or false, then suddenly I generate 8 tests. Okay, so if you want to be exhaustive, you're going to probably lose a lot of points at exam. I'm not saying that sometimes it's not good to be exhaustive. I'm just saying that during the exam, I'm going to try to test whether you are capable to apply this logic that we went through together. So I want to see you work smart, not hard. I want to see you figure out exactly what is the minimum amount of tests that gives you a good confidence that your program is operating correctly. Okay? And I say a good confidence. I do not say that you proved that your program is operating correctly. There's a big difference, okay? If you're interested in theoretical computer science, etc., theorem proving, program proving, and stuff like that, this is an open-ended area of research. We can assess some property of program, but the general problem of proving a program to be right or wrong is very, very difficult. Okay, we have to simplify a lot of things to be able to do anything at all. So it's almost an impossible task right now. So that's why I'm not using the word, I proved my program works. No, I just try to generate enough confidence that actually my program is doing its job by testing all the parts of the code. And for each time where I find myself with an interval, I assume linearity of behavior, and I try to test the boundary of the interval. And these are going to be the two main, these are not the only things that we're going to test in this class, but I would say that if by the end of this module you have a clear idea of what these two different tests do, and you systematically try to use them, not every program is going to require you to do code coverage or boundary testing, but it's good to try to think about whether you need it or not every single time, okay? If you do that, you are probably in very, very good shape, not only for testing, for your testing skill, obviously, but you're going to see how this is fundamental to even refactoring or debugging, okay? So that's what we're going to do next. Next, we are going to, let me scroll my notes real quick. Next, we are going to talk about refactoring. So refactoring, I'm going to kind of merge together refactoring and debugging because I want to give you different examples of refactoring first, and I want to use this idea of, logical, not logical table. This idea of test table, like we have been designing it right now, to help you assess, whether a refactoring is good or not. What does that mean, good or bad refactoring? Well, you know that when you refactor, you do plenty of things, okay? In this course, I even put under the umbrella of the generic term refactoring things like commenting, indenting. We don't have to worry too much about commenting and indenting right now because we use Raptor. When we use Java, we'll talk some more about that, okay? But also, refactoring can mean that you rewrite your code to make it more readable, to make it simpler, okay? And there was another good question in the forum about, is it better to use a complicated Boolean expression in one if statement or use multiple if statements? Well, these are the questions you address during refactoring. Assuming your program does always the same thing, okay? Remember, refactoring, we don't change the feature set of the program. We don't change its behavior. We just change implementation while keeping the behavior constant. So assuming that your behavior is the same, refactoring is a matter of style, it's a matter of simplicity, readability, ease of maintenance, your code is more extensible, it's easier to scale it up to different size of problem. All of those are things that go into refactoring. But the first step is to make sure that you didn't break anything, that you didn't change the behavior of your program. How do we do that? With tests. So you develop your code, you develop your tests, right? And then when you try to refactor, when your program is working, passing all the tests, you try to think hard about whether you need more tests or less tests. And then once you get that settled, then you start refactoring and you start wondering, if you can improve your code. And if you can improve your code, you immediately reapply all the tests that you have designed in order to make sure that none of the tests that was successful so far is now breaking. That's the idea of refactoring. But let me take a few examples here of refactoring with if statement. Okay, so I'm going to be lazy. I'm going to do a quick cut and paste. The benefit is that it would be probably more readable than my handwriting. Is this too small, or do I need to make this bigger? Let me know a little bit here. Okay, fine for one of you. I'm assuming that if it's not fine, don't hesitate to... okay, fine for two of you, that should be good then. Don't hesitate to mention if something is unreadable or something like that, okay? It's a pain to go through a lecture where you cannot follow because something is too small. It's easy to fix. Okay, so here's some code. So I have some code here, and what I want to do is I want to illustrate, refactoring. So I'm going to take this code first, and then I'm going to take this code. So what I'm doing here, by the way, the number 1 here that is highlighted in yellow, it could be anything. It could be one line of code, like a put hello world. It could be an entire program with like 10 if statements nested in one to another. Doesn't matter. It's a block of code. It's a piece of program. So what I'm focusing on here, I said that I have a program that tests if A is lesser than 3. If that's true, it executes whatever code block number 1, is represents. So whatever part of the code that I label number 1. And then later, I test, after the end of my first if statement, I test if variable b is lesser than 5, and it's true, I execute exactly the same code. So what you see as number 1 here and number 1 here is exactly the same code that I typed again in Raptor, and put in the then branch of those two if statements. So these are two if statements that are serially arranged. And my proposition is I'm going to take them, and I'm going to write something that is a lot simpler. Okay, you can see that the code here that I call number 1 appears only one time. For a programmer, it's really good to avoid redundancy. Okay, if you write the same code here and here, here's the problem that you have. In 6 months, somebody else, or you maybe, if you forgot enough about your code, or an intern, is going to look at this code and is going to say, oh, there's a bug here. I can fix a bug. And then that person is really happy, compiles the program, turn it into production, and then what happened is that they didn't realize that you were using the same code here and here. So this code here, no fix. Okay? It's really easy to forget that kind of thing. Imagine that you do even worse. You have that code labeled number 1. You have it copied all over the place, like, I don't know, 10 times in a program that's like 10,000 lines of code. How are you going to remember that the 10 location you have to modify? So this is really bad programming. Okay, this is something that's going to cost you points at the exam. When we deal with Java, we're going to learn to use function methods. That's going to allow us to alleviate this. Okay, but the idea that I'm trying to push onto you right now is that every time you cut and paste a block of code, it's a bad idea, even if it's just one formula. Okay, it's really poorly maintainable code. So that's why here, I want to refactor. And the way I'm going to refactor by obviously having the code number 1, whatever it is, written only one time. And this is my proposal here. I just say, well, here I trigger code 1 if this condition is true. If this condition is true, I trigger code 1. So what I'm saying is that if this condition or that condition is true, refer you back to the video lecture, okay, then I trigger code 1. Okay, and you have here 2 pieces of code. So my question to you now is, are they equivalent? What do you think? Okay, I have a yes. Anybody else? Okay. I don't know. Okay, you forced me to add a column. Very good. All right. We have 1 I don't know. Yes. Okay. Yes. Okay. So how many people in the room? 3, 6. We have 4 so far that are for yes. 1 that is, well, I'm not sure. And a second that says, I'm not sure yet. So 2. All right, 2 and 4. Okay. I can guarantee you that if I look at this and I'm in a hurry, or I'm just thinking about everything, or it's just a detail, or overestimate, how many times I've been dealing with a statement like that, I will get it wrong too. All right? It's just because this is a nest. This example here is a great example of a stupid mistake. And the mistakes are rarely stupid. People rarely say, I made a mistake so smart I'm going to patent it, right? And I'm going to sell it. So you never hear that kind of stuff. So I'm not saying stupid mistake to be, excessive or whatever. I'm just saying that, yeah, most mistakes are like, silly overlooking stuff or things like that. So in this case, yeah, it's silly, but it's interesting. That's why I chose this example. So let's take a look. How do we figure out? And that's most important, okay? It doesn't matter if you're right or wrong, but it matters if you have a process to determine things safely, okay? Because each one of us can think on that problem, take a look, and come to a conclusion. But if we have a process that everybody can repeat, everybody can replicate, okay, to double check that we were right or not. Well, it's the same idea. Then you look at like a demonstration in mathematics, and you say, well, this is trivial. I'll leave the demonstration to the reader, right? Fermat theorem, anyone? But then again, you look at it 6 months later, you forgot how you sorted it out, or maybe you were just thinking at a too high level and you didn't go through all the steps, and you made a mistake, and so on and so forth. So nothing beats a full demonstration, step-by-step demonstration that everybody can go and double-check, verify. Okay. So in our case, how are we going to do this? Well, all right, let's do the same thing that we did for the previous example, okay? Here are my if statement. I have first if statement here, so I'm going to number them, okay? I'm not going to call them top and left and right. I'm going to call them number 1, number 2, okay? And these are my execution paths. So number 1 can be true, and then number 2 can be true or false. Number 1 can be false, and then number 2 can be true or false. So given 2 if statement, okay, this is not really a testing table yet. It's just my attempt to try to understand, the different paths of execution. I can go inside the first if statement, or I can skip it. That's 2 paths. And then I can go inside the second if statement, or I can skip it. That's 2 more paths. So 4 paths total. That's what this table is telling me for now. Okay. In terms of input, let's try to map that into test, okay? If a lesser than 3, for a to be lesser than 3, that would mean, for example, 2, okay? 2 would be good. I'm going to remove this line because it's making the whole thing slanty. Okay, so 2 would be good, okay? Now, for the second if statement to be true, that would mean that b is lesser than 5, so I'm going to use 4. And because it's lesser strict, if I want the statement to be false, I can use 5. Okay, this is the idea of boundary testing again. Okay, nothing new there. All right, what about this case here where the first if statement is false? Well, if I have a 3, again, boundary testing, I stick to the boundaries, then this first if statement is going to be false, and then the second if statement is going to be true with, well, I'm going to keep the same number, okay, 4 and 5, except that here, let me see. If my first if statement is false and then my second if statement is true, yeah, I can keep 4 and 5. Yeah, never mind. I was going to say something else, but I'm going to keep 4 and 5. Now, what happens? So what is expected behavior? Well, let's take a look. And I'm going to try again. There we go. So let's take a look. If the first if statement right here is true, okay, what I'm going to execute is code number 1. All right. Then what? So if statement is true, I execute code number 1. Then I am done with my if statement. And then I look at the second if statement, because remember, they are serially arranged, right? They are not nested. That's where the trap was. So the second if statement here, well, let's see. It is true as well on this line of my testing. What do I do when it's true? I execute again code number 1. So if that displayed, yeah, there we go. Somebody in the chat window just said, "Oh, I see it now." That's the one trick of this example, okay? But it's sneaky. It's really sneaky. You can even use it if you're like a little bit sadist. You can use it on instructors, and see how long it takes them to catch and stuff. Because there is something very intuitive about going from serially arranged to or, because it's one or the other. But it's not one or the other. When you have serially arranged statement, if statement, you can have one and the other, right? You can trigger both, especially if the variable and the condition are not mutually exclusive, and that's what's happening here. So now that we have the funny part, out of the way, well, let's go a little faster on the rest. Let's see, second line of the code, I have a 2 for input, so that means that my first if statement is true. So I execute the code 1, but then I never enter the second if statement. Okay, it's false. Value 5, I don't get into it, so I don't do anything else. Then if my first if statement is false, I never execute that code here. But depending on whether the second is true or false, I might execute actually that version of the code here, or I might do simply nothing. Okay, there is a case here where I don't do anything at all. Okay. But this is exactly it. This is the trick. Now, if I want to look at this, and this is how you do it, okay? If you want to be 100% sure, you need to do those tables. I know it takes time, but this is how you learn. This is how you prevent, you know, making mistakes, okay? This is how you do it right. And everything else opens you to this vulnerability of us thinking too fast or at a too high level without paying attention to detail and making mistakes. The detail is the devil is really in the detail with programming. Okay, you cannot go too fast and reason at a too high level. You can do that after years and years and years and years of practice if you do programming 24/7 and you do always the same type of stuff. But anytime you face a new problem, you will have to slow down and go back to your foundation, okay, which is tracing tables and stuff like that. So let's take a look here, okay. This is my one if statement, actually, no plural, okay. My one if statement, I'm going to do a truth table where I look at the truth of this expression, then this expression, and then I do a logical OR between the two, and that gives me, you know, the whole expression. So you've seen an example of that in the video lecture. So a lesser than 3, let's go. True, true, false, true, false, true, false. Okay, all the possibility. So one thing to note already is that this guy has 4 execution paths on top, right? This guy has 4 execution paths too. So it's a good sign. That means that they are, I would say, somewhat equivalent. Okay, they have preserved the same amount, the same number of execution paths between the two code example. So now I'm going to do a logical OR between the two. So true or true is true. As long as one of the two is true, I get a true. When both of them are false, I get a false. This is the logical truth table. This is a truth table, sorry, for the logical OR operator. Okay? Question in the chat window. Will we have time allotted to prepare test table for quiz of exam? That's actually a good question. For exams, definitely, because the way that the exams are going to be managed, we don't have a time limit on exams. For the quizzes, that's a very good question. You should have enough time. If I see a pandemic, you know, a failure in a quiz, generally I try to figure out what happened. Okay, so don't hesitate to contact me and tell me, you know, I could not complete this question because of time. I doubt this is going to happen because generally I always try to overshoot the time by a factor of 2, you know, during the quiz. So let's say that you have, you know, you have like 10 questions or something like that. If these are like yes/no questions that you should be able to do in 30 seconds, generally I'm going to give like 5 minutes for each question. So it's not even a factor 2. It's I really try to overshoot. Okay, but sometimes a mistake is possible. But practice, you know, making those kind of tables as much as you can, because it's going to help you gain a little bit of speed. And even for the speed, it's not really our objective for this intro to programming. It's going to also help you get it done right the first time. Because the worst that can happen is if you do a truth table and you somehow mess it up, then you have to debug your truth table. So you have to start, you know, getting into that programming loop that I described, you know, hypothesis, implementation, validation, etc. But for the very tool that you use to debug something. So it's going to go insanely more complicated very fast, okay? And it's going to take a lot of time. So it's better to go slow and get it right the first time. This is where the quiz would give you max credit, than to try to go too fast and then get it wrong. Then you have to spend 5 minutes on that one question just debugging your truth table, okay? I hope it addressed your question. Let me know if I didn't address it fully. Okay, you must welcome. But don't worry about like inexperience. This is a first-time programming course, so you know don't feel bad or feel like, oh, I'm not experienced. You know, I'm going to need more help. No. This course is meant for people that are programming for the first time. Okay, so don't worry about that. You're right in the right course, and everything is designed in this course for first-time programmer, novice programmers. Okay, no worry there. All right. So let's go back here. What did we have? We had like the beginning of a test table that was more like list of the execution path so far. Now what we're going to add onto that, we are going to add our inputs. Okay, so I'm going to use the same thing. So let's see. I'm going to use 2 here. So input for A and B. I should have mentioned that. Sorry about that. So let me correct this here too. This is going to be variable A, this is going to be variable B, and these are my inputs. Okay, so we've, let me double check that this is correct, okay? We've a 2 for A, 2 is lesser than 3, so this is going to be true, okay? So I can use the value 2 here for those 2 lines where A lesser than 3 needs to be true. And then when A lesser than 3 needs to be false, I'm going to use the value 3, okay? Again, I stick to the boundaries. So this is for true, this is for false. Now I'm going to look at B. For B lesser than 5, okay, I can use 4. So I can use 4 here, I can use 4 here. And some of those lines are really not relevant because we don't go into each branch, but let's follow a routine for now, and then we'll simplify, okay? And then B lesser strict than 5 being false, well, I could use 5. Okay, so that gives me concrete values to actually test those different execution paths. And then the last thing I need is really what do I expect to happen. Okay, so let's see. If it's an OR statement, right? So if I do the logical OR between those 2 conditions here, there are 3 conditions here. Okay, there are 3 conditions here where I'm going to enter my if statement. I'm going to branch into the then part of my if statement. So that means executing number 1. And then there is this 1 here where both are false. So false or false is false. And this is going to give me nothing. And then I compare the 2 tables. Okay? And if I compare line per line, this checks out, same thing, and this is the problem. Okay, so it took a little bit of time, and it's one of those things where if I give that specific problem to all of you at an exam or something like that, somebody can get it right immediately. Somebody can, you know, like have to do the table to get it right. Somebody can try to skip the table and get it wrong. But the funny thing is that if I gave the same problem to all of you multiple times, let's say this year and next year, it's not even sure that consistently the people who got it wrong would get it wrong the same way. Okay, and that is a problem with skipping steps and trying to overthink it, you know, in a way of speaking. Okay, trying to just rely on your intuition. No, this is a beginning programming course, so we are going to try to do things by the book until we do them often enough that we build those intuition and reflex. And you will see that even when you're like a pro programmer, if you want to go into programming, this kind of silly mistake is going to always creep up in a project sometime, and no matter how good you are, you're going to overlook it one day or the other. Okay, and when something happens like that, trace. Okay, question in the chat window: is it wrong because the first and /if showed the message twice? Well, it's wrong. It's wrong because the 2 pieces of code are not equivalent. That's why it's wrong. And you're right. This is the difference between them. Okay, here. There is, like if I look at what happens, okay, here nothing happens. It's the same execution path for both programs, so that's good, okay. Execution of one time and one time, yep, that's here. And then execution of the code number 1 2 times in a row never happens here, okay. That's the difference. You're right. So that's why those programs, it's not necessarily that one is wrong and the other is right. It's just that they are not equivalent. So we are talking about refactoring, right? So if I ask you at an exam, here's a piece of code up there, and here's a piece of code down there. This is my refactoring. What do you think? Okay, or is it a good refactoring? You can answer and you can say, yes, it's a great refactoring because, you know, there is only one condition, and the code labeled number 1 is not duplicated, so there's no redundancy. It's a great refactoring. And this looks like a good answer, right? Because you caught like a few things that were actually very appealing about that refactoring. Unfortunately, you missed the one thing that we cannot do without in refactoring, which is the code need to be equivalent. The code need to behave the same way. Okay? So that gives you just one example of type of refactoring question, or I could ask you, here's the code up here, this code is really redundant. And I can be sneaky, I can say, this code is really redundant. We're using the code number 1 twice, this is unacceptable. How would you refactor this? And then you may have to provide me with the code that represents a refactoring. This would be the code to avoid, okay? Because this is not doing the job properly. All right. So, let's take another example. So let me scroll down my notes. All right, and I need a new page here. So this is going to be, again, refactoring. So let me write this here. So this is going to be another example of refactoring, okay? So, and we cannot cover like every single possible example, okay? Again, that's the nature of programming. But I can try to give you diversified enough examples that they illustrate common traps, okay, common problem. And that's a way not only to understand better, what this is all about, but it's also a way to prepare for the exam, okay? So that's what those live sessions are for. So let me take another example here. So here's a piece of code. It has, let's see, it has one if statement with else part, okay, at the top. And then it has a nested if statement in the then part of the first if statement. And then at the bottom, again, same proposition, I want to refactor. Okay, so I want to simplify. I want to move from multiple if statements that are nested, which is long to read, to something a little shorter. So let's go. Let's have a round again to see if this time we have something that works. So let me know in the chat window whether you think that these two pieces of code are equivalent, so that would be yes. They are not equivalent, that would be no. Or if you are unsure, take your time but to come to a conclusion. But if really you cannot tell them apart, then let me know, and I'll count that as a don't know for now. Okay? So take your time, no rush. Read this code, and let me know what you think when you're ready. Good comment. I need to see a truth table. Yep. Take your time. If you want to try to prepare a truth table, go for it. I'm not trying to rush through this. These live sessions are really, the more interaction we have, the better. So take your time, take a piece of paper, do a truth table. I'm going nowhere. Okay, don't worry. And people who are watching that after the fact, you guys can speed fast forward, through the time where we are doing those kind of things and just go to the solution. Okay, that's not a problem for anybody. So take your time, Eric, and let me know when you have an idea. And I'm just keeping track of how many people say yes, how many people say no. Yes. So let me scroll back to count here. 1, 2, 3, 4 yes for now. Again, take your time, guys. Well, question. If I'm assuming that if B is not less than 5, then it moves to else number 3. If B is... Nope. Let me which one? The top one or the bottom one? Before I say nope, I should have asked that. The top one, okay. So the top one, if our example is b is not less than 5, so that means let's say b equals 5, okay? B equals 5. This if statement, if it triggers, I go here, okay? Because b is not equal to 5, I go here, okay? Which is right before the end of the then part, and then I jump out of the if statement. I don't go in the else statement. Okay. To go in the else statement, I need to have, like, for example, in this example, a was 2. Okay. To be able to go into that else statement, I need something like a equal 3, or 4, or 5. Okay. That's the only way. Oh, okay. All right. So we have a change to no. Perfect. You see how tracing is important, right? It's because here we're talking about refactoring, so we're talking about a different skill. But the way that we decide about refactoring is by using tracing and testing. So that kind of gives you an idea of how the skills are like piggy riding on one another, right? It's not like we can learn one and then forget it, then learn the second, then forget it, and move to the third. We have to keep all those 5 or 6 skills, constantly up to par, so we can actually use each of them. They are very interdependent, and that is what makes programming a little bit difficult. So if b is greater than 5, we skip the else statement. Well, that else statement here, right here. Hold on, let me find my pen. That's not the pen. All right, that else statement here. The only way, just for something in the chat we notice all. The only way that we are going to trigger that else statement is if a lesser than 3 is false. Okay, that's the only way. So that doesn't really do anything to b, right? And yes, Michael, absolutely, yeah. That's why we do that. Okay. Again, everybody can generate this. Even good programmers. I'm not trying to bash on people who make a mistake here. Even good programmer will do that mistake occasionally. I'll certainly do it. More than occasionally, I guess. But that's just so easy. That's just so tempting. Okay. So another change to no. So now it's funny because we are 2 yes for 2 no. Isn't that interesting? This is like what? 1, 2, 3, 4, 5, 6, 7. 7 line of code here, 4 line of code here. Okay. So next time you're using your smart TV, and your smart TV crashes and you have to reboot it, remember this. Okay. Remember how hard sometimes it is to figure out our way through 11 line of code. So now imagine that you have like 500,000 line of code for your smart TV. Software engineering has a problem, right? Okay, another switch to no. I'm assuming, Cesar, you're switching from yes to no, right? Oh, no is your first answer. Okay, never mind, sorry. Yeah, I should definitely use the polling feature of Blackboard Collaborate. I just haven't used it in so many years that I was kind of like trying to avoid spending the time on it, but that would be probably better. Okay, well, let's try to take a look together. Okay. Again, only way, like one of you mentioned, like only way is I need a truth table. Yeah, that's correct. We need to do that truth table. So the first thing was to understand really how the code worked. So without understanding how the code worked, there's nothing we can do. So that was the tracing, and you guys have had very good question about, so what happened exactly, okay? So now we use tracing to understand exactly what the code does. Now we need to use testing to check that those 2 pieces of code are actually equivalent. So let's try something. Okay, I'm going to try to save us a little bit of time. Bear with me. I'm going to try to cut and paste this table here. I have no idea how it's going to look, so let's try. Well, it's not as good as it should, but I think we can work with that. So hold on. Let me remove the stuff we don't use here. Behavior. I'm just going to keep the expected column here. So I don't know if this thing would let me. No, probably not. And there is stuff missing here. Sorry about that. Hold on. Let me try again. Let's say this never happened. Let's deny. Let's use good old denial here. Alright, try again. Let's see if that works better. There we go. That's a little bit better. Okay, so what I have here is it's the same kind of test table, okay? So I have my outer and inner if statement. This is how I chose to label them, but I could have used, 1 and 2 here. The outer if statement is the one that is here, okay, the one that surrounds the other one, and the inner if statement is the one that's right here, okay, just so that you know. So true, true, false, false, true, false, these are all the possibility again, okay. I'm just going blindly through everything that could possibly happen. And then what? And then I convert that into input values. So values for A and B that are matching the true, false, okay? So 2, 4, 2, 5, 3, not applicable. Why did I write not applicable? Oh yeah, if the outer if statement is false, I go to my else part, and there is not an inner if statement in the else part. So the value of B really doesn't do anything. But I could use 4 and 5, okay, just for the sake of my test table. That's not a problem. If I had to enter A and B beforehand, I would have to enter a value, so I would use 4 and 5 here. All right. And that was the outcome, the expected behavior. So if the first if is true, we get into the then part. If the second if is true, then we display number 1. I mean, we display number 1. Sorry, we execute code number 1, whatever it does. Great. Now, what if the first condition here is true? So we go in here. But then the second if statement is false, so B is not actually lesser strict than 5. Then I execute whatever is between this and if, right, and the else. And there's nothing here. Where I typed XXX, there is nothing. So I really don't do anything, okay? I don't execute any over specific part of code, that's what I mean. And then the same way, if my outer if is false, all right, so I end up in the else statement here, I execute code labeled number 3, and I just do code number 3 no matter, what happened with the value of B. The value of B is not even tested, so that would be number 3 here for those 2 cases at the bottom. So 3 possible outcome, okay, I execute code number 1, execute code number 3, or I do nothing. All right. Now let's take a look at this guy here. Same thing. I'm going to go and fetch the test table. All right. And I'm going to try to do another cut and paste. All right. So as we did before, okay, I look at the condition A lesser than 3. So it's a composite multi-term Boolean expression. So A lesser than 3 is the first term, then B lesser than 5. And then here, this is the whole thing, okay, the AND, whoa, that's big, the AND, logical AND between the two, okay. So I go through all the possibilities just like I did above, okay. So A lesser than 3 correspond to my outer if statement, B lesser than 5 correspond to my inner if statement, if you're trying to make the link between the two examples. So when I do AND of all the possibilities, that's what I get, okay. Logical AND, the truth table, means that something is true. The AND expression is true only if both parties are true, both terms. So I have one true here and then a bunch of false. So that means that for that true here, I'm going to enter the then part of my else, execute code number 1. Well, I look at the value 2 and 4, 2 and 4 here. This is the same stuff. Very good. Now let me jump to the other one that works, right? When A lesser than 3 is false, no matter the value of B, I'm going to go to the else. I'm going to execute code number 3. Very good. That's what I did here too. And then here comes a little subtle difference that makes us make a mistake in that piece of code. If A lesser than 3 is true, B lesser than 5 is false. So the end of both of them, end of true and false, is false. Okay, so I go in the else statement. My condition is false, I go to the else statement. I execute number 3. Oops, that was bad. Okay, there we go. What happens here now for the same test? Okay, 2 and 5. Okay, 2 and 5. A lesser than 3 is true. B lesser than 5 is actually false. In this code, nothing happens. So let's review. Okay, A is 2. So 2 lesser than 3 is true. So I come here in the inner if statement. But then B is 5. So B lesser than 5 is false. And so I don't do anything. So that's the difference between the two pieces of code. Okay. And again, it's not trivial to spot. Okay, like one of you said earlier, I need a truth table. You're not alone. Everybody needs a truth table. Again, if you keep doing that, every day of the week for like a few months, then you're going to become so good at it that you're going to be like a machine, right? But if you just use that on and off, every other week, every month or so, you don't deal with a lot of Boolean algebra problem or Boolean expressions that are complicated in your code, then this is a skill that's going to erode itself. So it doesn't matter how good or bad you are at it. It matters that you have a method to get it to work, when you need it to work, even if it takes a little bit more time. Okay, I'm going to take one last example because, refactoring is tricky. So I want to make sure I give you a good diversity of example and situation where it's not really working. So let's take this example here. Again, cut and pasting, being lazy. There we go. And let's take another piece of code that's supposed to be equivalent. There we go. So let's be adventurous, okay? I think I have a yes/no polling enabled. So you should have a yes and a no button somewhere. It's right above the participant list. That icon that looks like a checkbox that's checked actually. If you put your mouse on top, it says yes or no or none. Okay, and you can answer like that. You can, like for example, I just selected yes. I can go back and select no. I can go back and select none. Okay, so please use that to let me know if yes, those two pieces of code are equivalent, or no, they are not equivalent, or just leave it at none, if you are not sure. Okay, and feel free to type in the chat window if you have comments or questions. So the first step, right, is tracing, figuring out we're all clear on what's happening, and then we are going to start like taking a piece of paper, scribbling in like one of those truth tables, try to figure out, exactly what's going on in the first program, and then figure out what's going on in the second program. So take your time, no rush, okay? Everybody watching the video afterward, feel free to skip forward when you see me actually draw the solution of the tables, okay? Okay, I've got a no right now. I'll keep you guys updated as I see responses coming in. Another no, so we have 2 no right now. Ah, 3 no's, okay. And while you guys think about it, I'm going to start. I cannot cut and paste the table for some reason, so I'm going to start writing it. It's going to take me a little bit of time while you guys finish deciding. So I'm just getting rid of the boilerplate work here, right? True, false, false. Okay, we have four nodes for now. This is really the same type of table. I'm even using the same value actually. Same values. So then expected. Three, four, five. So we have 5 nodes so far. So it's getting terribly in favor of the nodes. Somebody's typing a question. Okay, no as well. So I think we are at 100% no. Okay, there's still somebody typing something here, question maybe. So just like take your time, and when you're done, I'll address it. Okay, keep an eye on the chat window. But let's try to figure out. So it's unanimous. Okay, these two pieces of code are not equivalent. Question is A lesser? Yes. Blackboard Collaborate likes to try to replace symbols we use in programming by emoticons. So I don't know which symbol has been triggering. Oh yeah, lesser than 3. Okay, heart, never mind. So if A lesser than 3 and B greater or equal to 5 gives a different output. No, it's okay. It's not you. It's Blackboard Collaborate. Don't worry about that. Okay, so you say that they are not equivalent, right? And this is a case that you have to illustrate that, right? Okay, cool. I understood that. All right, so let's take a look together, right? We are going to take this. All right, so I took the different paths. I took values to illustrate each of those paths to trigger them. Now I want to go through and figure out what happened. So first line is A equal 2. So A equal 2 means that this is true. So I go in the inner if statement. And B equals 4. 4 is lesser than 5, so it's true. So I execute code number 1. Okay, that's the first one. Number 2, A lesser than 3 is 2. A is 2, so it's still true. So I go still in this inner if statement. Then my B is 5, which is not lesser than 5, right? So I go into the else statement of that second if, and that means I execute code number 2. All right, so far so good. Now, if A is equal to 3, that means that A lesser than 3 is false. So I skip all of this, right? And I always go to the else statement. So I execute number 3 here. I execute number 3 here. Okay? All right. Let me clean up. I'm going to try to use the same table. I'm just going to change ink color. Okay? We'll see how it turns out. I hope it's going to be readable. I'm going to use here number 1 to represent this condition, and then number 2 to represent this condition. Okay? So a lesser than 3, the same thing. B lesser than 5, same thing than before. Okay? Now I have another term that I didn't have before. It's b greater or equal to 5, but it just happens to be the opposite of b lesser than 5. So every time I have a true here, I'm going to have a false. Every time I have a false, I'm going to have a true. And that would be b greater or equal to 5. Okay? All right, so let's look at number 1 here. So it's an AND statement between a lesser than 3 and b lesser than 5. So true and true, the AND statement is going to be true. Then everything else is going to be false, because one of the two, at least one of the two, is going to be false. Okay. What do we have here? At number 2, we have an AND statement as well. Okay. So the AND statement is between a lesser than 3 and b greater or equal to 5. So when both of those are true, then I have a true. That happens here. Okay, this is true, this is true. And then the rest of the time, I have false. So now I have here a summary pretty much of whenever I get into my first, then part of the first if statement, whenever I get into the else, and then same thing for the second if statement. Okay, so let's see what's happening. So, first if statement is true. I'm right here. Well, I'm going inside this. At the then part, and then there's nothing else. So I'm doing number 1 here is executed. Okay? Then what? Second line. The first if statement is true. So I go in the then part as well. What happened with the b, etc. is irrelevant. Okay? I'm still going here, number 1. Okay? A lesser than number 1 here. Number 1 here is not true. What am I saying? Sorry about that, guys. I was looking at a lesser than 3 like I've been doing for the previous example. So I'm here. Let me force my attention here on this one. I'm looking at the first if statement. If it's true, I go into then, I execute number 1. If it's false, which it is false here, okay? So if it's false, I go to the else. Then what happens is my else statement. My second condition is true. So I end up here, in the then statement here, executing number 2. Okay, so far so good, right? All right, try again. Number 1 is false. So from now on, it's going to be always false. So all of this is really irrelevant. I always end up in the else statement. Then we look at the second if statement, and this time it is false. If it is false, I go to the else, which means I execute number 3. Right? And then the last line. The first if statement is false, so like I said, we go in the else, okay, and then this guy is false again, and then I execute number 3. Alright, these guys are equivalent. If we do the truth table, they don't look equivalent. There's something there that is actually misleading, again, but that's why those examples are good, right? It's because they are misleading. But if you look at the truth table, then you realize that they are equivalent. So that should not be reassuring right now from the exam, right? Some of you might be thinking, oh my God, what's going to happen there? Well, again, being right or wrong doesn't really matter. What matters, again, is that you have a method, okay? Because the method will not let you down if you apply it and if you learn to apply it. And a comment in the chat window that say, I need practice. Yeah, but that's a good thing, right? Because it's really easy. It's really easy when you read something or when you watch a video lecture, you know, like the video lecture for this this module. it's, you know, you follow, everything makes sense, it's great, you know, everything. Well, actually, this lecture is a bad example because there is one weird trash can going on there. But a normal lecture where the lecturer doesn't misunderstand how to operate a trash can, then you can follow it very peacefully. You know, it doesn't challenge you, it doesn't give you any brain cramp or anything like that, and then you think that you are comfortable with the material. But most of the time, no matter how good the lecture, no matter how good the book, no matter how good the explanation, until you try to apply it to certain problems that are tricky, you're not going to realize how much you know or how much you don't know. So that's hopefully what the practice exercises are going to do for this course, okay? The practice exercises are meant to challenge you. I don't give you the solution. So they are meant to challenge you to make sure that you understand everything. For module 101, 102, 103, I must admit the practice exercises are really aligned with the apprenticeship exercise, so that they might not be as much of a challenge. So that's why during those lectures we're going to try to look at the extreme case and connect it all back to the skills, okay? We're going to try to pretty much shake your understanding until something breaks. And it's actually a very good thing when something breaks, because that tells you exactly what you misunderstood. So when you program, okay, when you write programs, you're going to have half of your brain trying to write the program, and the other half of your brain is going to try desperately to find tests that are going to fail your program. Okay, and this is a way for you to challenge yourself, to play against yourself. Okay, if you do that, you're going to go a little slower at the beginning, but you are going to produce much better code. Okay, and it's something that's useful in programming. But as I already hinted, you know, like a few weeks ago, no matter what you do in IT, whether it's system administration, database, web, programming, anything, this ability to be able to challenge what you write at the moment you're writing it, or challenge what you design, no matter what it is, at the moment you design it, is really, really a good skill, a good mental skill to develop. Okay, and this is why we talk about testing. I don't want you to become a quality assurance professional. I'm not trying to teach you real world testing. We are just using testing as a tool to train our minds to question things. You know, to always question things and to always find the flaws in a piece of code or something like that. Again, those of you who are interested in security, and that's a lot of students recently, you should like that kind of way of thinking, because it's really what you do when you do penetration testing, or when you're trying to actively find exploit, right? You're trying to find the flaws in a system, and that's really what we do with testing. All right? Okay, and we are, I would say, almost done. We talked about refactoring. That took us a lot of time. So testing took us a little bit more time. Refactoring took us most of the session. Implementing, designing, just a few remarks. And I'm going to finish with debugging. Debugging is going to be just kind of like a few remarks, like just wrapping up what we have been doing tonight. Couple of things. What can go wrong with an if statement? Well, to summarize, it could be the way that you are nesting them, if there are more than one. Okay, so if, then, okay, else, and if. Okay, so nesting here or nesting here depends on the condition, whether it's true or false. Okay, the decision of nesting depends on what you're trying to achieve with your code. The choice between this and that. A first if statement here, and then a second if statement, which is serially arranged compared to the first one. That's a source of error. Okay, and these are the very big mistakes. So before you go into any detail, any truth table and stuff like that, you need to spend a good amount of time thinking about, you know, whether, like let's say that you have two if statements, whether you want the first one and the second one nested here, or the first one outside the second one nested here, or whether you want both of them one after the other. And I guess, let's call this alpha and beta. You could even have a question about whether you want beta before alpha. Okay, so that's one more possibility. And same thing here, let's call this alpha, and this would be where I put beta, first possibility, second possibility. Well, you could have also if condition beta, then alpha would be right here, so that would be another possibility. Else alpha would be here, that would be a second possibility. Okay, if you want to go exhaustive, thinking about everything that can happen, these are like all your choices with 2 if statement. So that's a bunch of choices, okay? It seems like there are a lot of possibilities, but you are not going to go into this blindly, okay? A computer trying to determine which one is the best would probably try them all or use some sort of heuristic, okay? You are an intelligent human being, so that means that you know what one if statement does. And you simulate in your head, okay, this is what's going to happen when I write an if statement, so now do I want my second if statement to be here? Hold on, trying to find my pen. Do I want it to be here, or separate? You're going to ask that question. You're going to think through that question, okay? Whether a machine would not be able to think through it, would just test everything or something like that, okay? So it's a lot of possibilities, but you think your way through selecting them. You don't go and explore them blindly, okay? So that's the first thing that can go wrong. The second thing that can go wrong, obviously, and we have been talking a lot about it, is your Boolean expression. So your Boolean expression doesn't represent what you mean. For example, you want to accept a value between 1 and 3, you write an if statement, you say if x is lesser strict than 1 and x greater strict than 3, well, guess what? You just wrote the exact opposite of what you meant to do, okay? So you're going to correct this, and you're going to say, well, okay, so this is like lesser than here, greater than here, and lesser than here, but guess what? Now you're off by 1 because you don't accept 1, you don't accept 3. So then you're going to correct yourself again, and this is what you're going to come up with, lesser than equal or greater than equal. So this is the second source of error. The good news is that you can use truth tables, okay, to check this. I mean, what I showed you today is really an hybrid between a truth table, a sort of bastard hybrid between a truth table and a test table, okay, but I think it's going to help you a lot, at least through module 101, 102, 103. After that, we'll adopt another approach, okay? But for now, I think that this kind of table, the way that I illustrated it tonight, might be the simplest, the most straightforward way for you to validate code, okay? So drawing those tables is actually essential, and it's going to allow you to take into account 2 things about testing. Very easily take into account the code coverage, because you look at all the possible paths. And inside each path, if you have an interval, then you're going to be able to take into consideration boundary values as well. Okay, so we illustrated the 2 main testing tricks that we are going to use in this whole semester. Okay, let me think. I think this is all. The only thing I can see on my note, it was a reminder. Make sure that you know what AND truth table is, what an OR truth table is. Okay, these are the 2 main that are useful for these modules on Raptor. But there is also something called the XOR, exclusive OR. The way that I mention XOR to my students generally is I explain to them that in some European restaurants you can choose between dessert or cheese at the end of your meal, right? So the logical OR means that you can have dessert or cheese or both. The exclusive OR, that's what X mean that you have to make an exclusive choice between the 2, which means you can have cheese or dessert, but you cannot have both. So what does that mean in terms of logic table? That means that when the 2 operands of your XOR are actually the same, for example, true and true, false and false, your XOR tells you false. When they are different, it tells you true. Okay, so replace true and false by cheese and dessert, and you get to the point where you can have actually one or the other, or one or the other, but not both at the same time. Okay, so that's the difference with the OR table, which I'm going to draw real quick here. The OR truth table says that if one of them is true, no matter which one, then you have a true. Otherwise, you have a false. Okay, you can see the difference between the 2. Okay, so write down on a piece of paper all exam and quiz are open books, so just organize your notes. Make sure that you have the truth table for the AND operator, the OR operator, and keep the XOR somewhere just in case it pops up in a quiz or exam. Okay, but once you have those 3 basic truth tables, and I'm going to add for sake of completion, for sake of completion, the AND truth table as well, which is true only when both operands are true. Okay, when you have those 3 basic tables, then you can decompose any Boolean expression step by step, but take your time. For those of you who already took discrete math, you already took Boolean algebra, so everything I went over tonight was hopefully a refresher for you, or it was utterly boring. I apologize if it was boring, but that's what happens when you know stuff, right? So discrete math is another course that's going to actually go much more in depth into those truth table and Boolean algebra in general. So as soon as you get that done, all those problems about programming are going to seem suddenly a lot easier, okay? But if you haven't taken discrete math, and why would you? It's not a prerequisite, okay? Then consider this your introduction to Boolean algebra, pretty much. Very, very basic, very, very start. Question in the chat window. I did not know that exam, open note, open book is that the same for quizzes? Yes. And yeah, absolutely. And the reason for that is that, think about it, in an online program, it's really difficult to enforce, closed book. So instead what we do is we ask questions that are a little above what we would ask if our goal was only for you to memorize things. So now, don't get me wrong, okay? I'm the first one to say programming is not about rote memorization, and we're trying to teach you skills that are at a much higher level, on a cognitive scale. So you can have an open book exam, that's not an impediment for me. But here's the thing, even though we don't test you on memorization by asking you to have closed book quiz and stuff like that, you need to memorize, some basic knowledge so that you can build on top of it and then do things that are more complicated, okay? It's like somebody who doesn't know what the square root symbol means. You cannot do math if you don't know the syntax, right? You cannot do programming without the syntax. So we are lucky. Raptor doesn't have a lot of syntax, but there are some base concepts you need to remember, okay? Because otherwise you're going to be constantly flipping through the page of your book or replaying video, etc. And it's going to take you so long that you're going to time out on every single quiz, and you are going to even have problems finishing the exam in 1 week, okay? So memorization is not the ultimate goal of this course, memorizing a bunch of facts, but you need to memorize, a lot of stuff to be able to do those higher level things, okay? And yes, it's a lot to remember. I mean, think about it. We have module 101, 102, 103. We have actually no syntax. Okay, Raptor doesn't have any syntax. Implementation is straightforward, but look at everything we had to go, to acquire a methodology to assess if two if statements are equivalent. So yeah, it's a lot of stuff. But if it was not a lot of stuff, you would probably wasting your tuition, right? Out of course you want to get a lot of skills that you didn't have before to enter the course. So if that happens, then you end up like on the winning side of taking a course. If you didn't have a lot of stuff new to learn, then yeah, probably not worth your time. But all right, okay, we are done with the main things that I wanted to cover during this session. So if somebody has questions that they want to ask and have on a recording, because they might be useful to other people, they will certainly be useful to other people, I'm game for that. I'm going to leave the floor open a few seconds. Make sure you start typing or you say something. And if I don't see anybody typing, then what I'm going to do is I'm going to stop the recording for tonight, and then I will hang around a little longer so that we can have a discussion about whatever you want to discuss. If it's a personal question, I can see you in a private room while the others are waiting their turn. So we can address all those questions now. So I see somebody is typing, so I'm going to wait to see if this is a question they want on the recording. Okay, question. Are we ever going to go over the tests after everyone has completed? The tests are not something that we go over in the live session. What we do in the live session, we wrap up every module, like Monday right before the deadline at 11:55 p.m. to make sure you have a good understanding and any pending question is addressed. But the test is something that you review one-on-one, okay? So if you have any question about the test, or more specifically about the feedback that was given to you in the test, you contact immediately our TA, because the TA is the one that does the grading for the test, and you copy me to the email. I really suggest that you use emails instead of Canvas messaging. We've had a few problems with Canvas messaging lately, so but just send an email using your USF email address to the TA, copy me on that email, ask as many details as you need, to understand the feedback, to make sure you don't make the same mistake. And if you need to meet one-on-one, with me as a TA, to go over something, then we'll do that. Okay, but that's how we are going to review the feedback for exams. All right. All right. Well, thank you everybody that not only took the time to attend. Again, that was a pretty long session. Thank you for attending. Thank you for participating actively. I really, really appreciate that. It's always a pleasure to be working with students interactively. Everybody who is going to listen to this video, if you have any question, use the forums. You know the drill. Okay, don't hesitate to use the forum to ask any question. And thank you also for listening to the entire video. Make sure that you listen to everything. Don't skip on some of the study material, because that can be dangerous for exams. Okay. And this being said, I am going to stop the recording for tonight. Have a good evening, everybody, and I'm going to hang around for Q&A if there are any questions. Okay. So have a good evening, everybody. Bye.